Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. A bank manager opens an email that looks like it's from IT. She clicks the link. Within hours, every customer record, names, social security numbers, account balances, is for sale on the dark web. The attackers didn't need a zero-day exploit or $1 million firewall bypass. The data was stored in plain text. No encryption. That single missing control turned a phishing click into a career-ending data breach. By the end of this video, you'll walk away with 3 concrete resume-worthy skills: choosing the right type of encryption for the job, reading a browser's padlock icon and understanding the protections behind it, and encrypting an actual file with OpenSSL. These aren't abstract concepts. They're the difference between entry-level support roles and higher-paying security analyst positions. But before we get hands-on, you need the core mental models. Encryption is everywhere, from the Wi-Fi in your home to the online banking in your pocket. And it's built on math, not mystery. Let's start with the simplest version that still stops an attacker cold. Picture this. Alice wants to send Bob a secret love letter. But Eve works in the mailroom and reads every piece of paper that passes through. So Alice shifts every letter forward by 3 places. Hello becomes Khoor. Bob, knowing the shift, reverses it. Eve sees only gibberish. That scrambling is encryption. The original readable hello is plain text. The scrambled Khoor is ciphertext. And the number 3, that's the key. Even this childishly simple system zeroes out the eavesdropper. Now imagine the math behind real-world encryption. Here's exactly what happened. The plaintext hello and the key of 3 flowed into a simple encryption algorithm. That algorithm shifted each letter forward by 3 positions. Out came Khoor, unreadable ciphertext. Without the key, it's just noise. Every encryption system on the planet follows this same blueprint, just with much scarier math. Let's lock in what we've covered so far with a quick check. Quick check before we move on. If a message has been scrambled by encryption, what do we call the unreadable output? Before we move on, notice something important. Even this simple Caesar cipher introduced 3 ideas you'll see throughout your IT career: plaintext, ciphertext, and a cryptographic key. Modern encryption uses far more sophisticated mathematics, but the core concept never changes. Data starts as readable information. An algorithm transforms it using a key, and the result becomes unreadable to anyone without the correct key. Keep those 3 pieces in mind. They're the foundation of everything that follows. All encryption falls into exactly 2 camps. Symmetric encryption uses one secret key that both parties share. It's lightning fast, but you have the hairy problem of securely getting that key to the other side. Asymmetric encryption uses a pair of mathematically linked keys: a public key anyone can see and a private key that stays secret. That arrangement elegantly solves the key-sharing nightmare, but it's slower. Every real-world system combines the 2, and that's exactly what we'll unpack next. In symmetric encryption, there's literally one key to rule them all. Alice encrypts the message with it, and Bob decrypts it with the exact same key. It's fast, it's efficient. But now ask, how does Alice get that key to Bob in the first place? If Eve intercepts the key during transmission, the whole system is broken. That's the classic key distribution problem, and it's why the industry standard, AES, is almost never used alone. We'll see how asymmetric encryption solves it next. AES, the Advanced Encryption Standard, is the workhorse of symmetric encryption. It typically uses 128-bit or 256-bit keys. AES 256 is so secure, the US government relies on it for protecting classified data. When you connect to a WPA2 Wi-Fi network, or when a disk encryption tool like BitLocker scrambles your hard drive, there's a good chance AES is doing the heavy lifting. Many VPNs also use it to keep your traffic private. Open your terminal. Here's how you'd encrypt a file with AES 256 in one command. The -AES 256 CBC flag tells OpenSSL to use AES in cipher block chaining mode, a modern, strong configuration. The -K flag lets you provide a password, and OpenSSL derives a 256-bit key from it. When you press Enter, a file named secret.yankee appears. Pure ciphertext, nothing readable. Without the password, it's garbage. Pause the video and think, what is the biggest weakness of symmetric encryption? Hint, it's not about the math. Alice wants to receive secret messages without sharing a secret key. Instead, she buys a padlock with a unique key she keeps. She sends Bob the unlocked padlock. Bob writes his message, puts it in a box, and locks it with Alice's padlock. Now even the mail carrier can't read it. Only Alice's key opens the lock. In digital terms, that padlock is her public key, and the key is her private key. This is public key cryptography, and it solves the massive headache of key distribution. RSA is the most famous asymmetric algorithm. You generate a key pair, a public key you share with the world, and a private key you guard with your life. Anyone can encrypt using your public key, but only you, with the private key, can decrypt. The security of RSA depends on one simple fact. Multiplying two huge prime numbers is easy, but factoring that product back into the original primes is brutally hard. Factoring a 2048-bit RSA key is beyond any known computing power today. That's why RSA is widely used in SSH connections and digital signatures to verify identity, alongside other supported algorithms. So you've got Bob's public key. How do you know it's really Bob's and not a hacker pretending to be Bob? That's the man-in-the-middle problem. The solution? Public Key Infrastructure, or PKI. It's a system where trusted third parties called certificate authorities digitally sign a certificate that binds a public key to an identity. Your browser or operating system already trusts a set of root CAs, so when a site presents a certificate signed by one of them, you can trust the public key inside. That's the chain of trust that underpins HTTPS, and we'll dive deeper later. Now, let's put everything together. When you visit a secure website, your browser first needs to establish a secure connection with the server. The server presents its digital certificate, allowing your browser to verify its identity. Once that identity is trusted, the browser and server securely establish a shared session key using modern key agreement techniques. Here's why this matters. Asymmetric cryptography is excellent for authentication and securely establishing shared secrets, but it's too computationally expensive to encrypt every web page, image, and video. Symmetric encryption, on the other hand, is incredibly fast. So after the session key has been established, both sides switch to a symmetric algorithm such as AES to encrypt all of the actual application data. Think of it like introducing yourself to someone with a government-issued ID. Once both of you know who you're talking to, You don't keep showing your ID every time you speak. You simply continue the conversation. That's exactly how modern TLS works. It uses asymmetric cryptography to establish trust, then relies on fast symmetric encryption for everything that follows. Let's see real encryption in your browser. Navigate to any HTTPS site and click that little padlock. In Chrome, you'll see Connection is secure. Click Certificate is valid to dig deeper. Under Details, you can see the public key algorithm, maybe RSA 2048 or ECC 256. And under Certification Path, you see the chain of trust, a root CA, an intermediate CA, and the site's certificate. This is the PKI infrastructure that verifies you're talking to the real bank, not a fake. We'll unpack all of that in Part 8. Time for a quick checkpoint. Imagine you're staring at a phishing page with that comforting padlock. What does that TLS encryption really give you? Here's a hint. It's not as much as you think. The answer: encryption protects your data's confidentiality on the wire, but it does absolutely nothing to prove the server's identity. A criminal can buy a certificate and encrypt your connection too. That's why we need certificate validation and a whole public key infrastructure, which we'll cover next. Keep that distinction in mind. Pop quiz. You hear envelope encryption tossed around in a cloud security interview. What exactly is it? Answer: it's a pattern where your actual data is encrypted with a unique data key, and then that data key is itself encrypted using a master key, the key encryption key, stored safely in a key management service or HSM. This way, even if someone steals the encrypted blob and the wrapped key, they can't unwrap anything without access to that master key. It's defense in depth for your encryption keys. Final check on key management. When you're building an app that encrypts data, where do you put the master key? The right answer: inside a key management service built for exactly this job, with strict access controls and audit logs. The wrong answer: buried in your source code. A KMS keeps keys safe, rotates them automatically, and lets you define who can do what. Lose control of that master key and all your encryption is for nothing. Let's test your understanding. When a browser connects to a secure website, both the client and server eventually begin encrypting data with the same symmetric session key. But here's the question: how do both sides obtain that shared key without exposing it to attackers? The answer is that modern TLS doesn't simply send the session key across the network. Instead, during the TLS handshake, the client and server use authenticated key agreement to securely establish the same shared secret while using the server's certificate to verify they're talking to the legitimate website. An attacker watching the traffic can see the handshake happen, but cannot calculate the shared session key. Once both sides have established that shared key, every web page, password, API request, and file transfer is protected using fast symmetric encryption like AES. That's the reason HTTPS can be both secure and fast. SSL is dead, and it's been dead for years. The old protocol that started it all was abandoned after serious vulnerabilities made it unsafe. Today, everything runs on its successor, Transport Layer Security, or TLS. The current version of TLS has stripped out all the weak ciphers and streamlined the handshake, making connections faster and far harder to attack. So when you see that padlock in your browser, it's TLS doing the heavy lifting, keeping your banking, email, and private messages truly private. Here's a mistake that will get you shredded in an interview: saying passwords are encrypted. Passwords are hashed. Encryption is reversible. Give me the key. I give you the data. Hashing is a one-way street. You feed in password 123. You get a fixed-length fingerprint. No key can turn that hash back into the original. You can only guess. If a database leaks encrypted passwords with the key, it's game over. If it leaks hashed passwords with salting, the attacker's job is brutal. Know the difference cold. Speed matters, and the difference is dramatic. AES 256, a symmetric algorithm, is extraordinarily fast, perfect for bulk encryption. RSA is significantly slower, so we only use it for key exchange and digital signatures. Now, elliptic curve cryptography, or ECC, reshuffles the deck. It provides security comparable to a much larger RSA key while computing many times faster. That's why modern TLS and mobile apps have shifted heavily to ECC for the handshake. Lower power, same trust, much better performance. If you remember one rule, make it this: never roll your own crypto. The WEP wireless standard from the early 2000s is the classic cautionary tale. Its flawed implementation let attackers recover the key in minutes. Today, we use WPA2 with AES CCMP and WPA3. The lesson: use standard peer-reviewed libraries, OpenSSL, libsodium, AWS Encryption SDK. Let mathematicians and cryptographers build the primitives. You assemble them like Lego blocks. Leave algorithm design to the PI. Encryption isn't some exotic specialty. It's baked into the tools you already use. BitLocker encrypts your entire drive using AES whenever your laptop is off. HTTPS secures every web visit through TLS. OpenVPN and WireGuard wrap your network traffic in encrypted tunnels. PGP protects email end-to-end. SQL Server's transparent data encryption locks down databases without you changing a line of code. And S3 server-side encryption safeguards cloud object with a simple setting. These are the silent guards working behind every click. One more myth to bust. You see the padlock, you feel safe. Is that right? Encryption is only as strong as your key management. You generate a key, then store it securely, never in source code. You rotate it on schedule, retiring old keys before they become a liability. And when it's time, you destroy it completely so nothing can be recovered. In the cloud, dedicated key management services and hardware security modules handle this lifecycle automatically, with fine-grained access controls and audit trails. Lose control of a key, and even AES 256 can't save you. Whoever holds the keys holds the kingdom. This chain is why you can type your bank's URL and trust the site. A root certificate authority, a company like Let's Encrypt or DigiCert, signs an intermediate CA's certificate. That intermediate signs your bank's server certificate. Your browser or OS inherently trusts the root CA. It follows the chain. Root vouches for intermediate, intermediate vouches for the website. If any link breaks, your browser throws a big red warning. This prevents an attacker from forging a certificate for yourbank.com. Part 8 dives deep into PKI. For now, just know the chain exists and guards every padlock. If you're working in healthcare, finance, or with European citizen data, encryption isn't just a best practice, it's often the law. Regulations like HIPAA require specific safeguards for protected health information. PCI DSS demands that cardholder data be stored unreadable. And privacy laws like GDPR carry heavy financial penalties for failing to protect personal data. This regulatory pressure creates constant demand for professionals who can design, implement, and audit encryption strategies. Compliance may not be glamorous, but it's a career cornerstone that never goes out of style. When an interviewer asks, What do you know about encryption? Don't say, I've heard of it. Lead with a structured answer that proves you can apply it. Memorize these 3 talking points. 1. Explain the TLS handshake, asymmetric key exchange, then symmetric session. 2. State clearly when you'd pick AES over RSA, bulk encryption versus key exchange. 3. Mention you've actually encrypted files with OpenSSL, not just read about it. That's the difference between sounding like a help desk candidate and a future security analyst. Entry-level SOC analysts can start in the 60 to 85,000 range. Security engineers climb into the mid-100,000s, and architect roles can blow past 190,000. These salary ranges are common across the industry, and encryption is a core competency that accelerates your move from the left bar to the right. You're not just learning a concept, you're building the skill that makes that jump possible. Let's bring everything together. You now understand that not all encryption works the same way. Symmetric encryption uses one shared secret and is incredibly fast, making it ideal for protecting large amounts of data. Asymmetric encryption uses a public and private key pair to solve the problem of securely establishing trust and shared secrets. Modern secure systems combine both. TLS uses asymmetric cryptography to authenticate identities and establish a shared session key, then switches to fast symmetric encryption to protect all application data. You also learned why encryption alone isn't enough. Protecting the keys is just as important as protecting the data itself. These are the concepts you'll encounter again and again in cloud computing, cybersecurity, networking, DevSecOps, and identity management. Let's make sure it sticks. Which encryption algorithm would you use for a fast, secure database at rest? Think about speed versus key exchange. In the next episode, we crack open public key infrastructure, the certificate authorities, the chain of trust, and how a tiny lock icon tells your browser a site is genuine. You've already seen the building blocks. Now we wire them together. If you can explain PKI in an interview, you're no longer entry level. Watch that one next. Link popping up on screen. Encryption isn't an optional add-on in IT. It's the table you sit at. You now know more about it than half the candidates interviewing for SOC roles. Keep building. And in the next video, we'll make that knowledge bulletproof with PKI. Smash like, hit subscribe, and grab the full masterclass playlist in the description. You've just leveled up. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson. Build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.